All right. So yeah, last time we talked about what was this section? I don't even remember the section anymore. 38? I think it's 38. But we talked about, clustering and stuff like that. And we talked about k-means, as a way to cluster, basically an unsupervised learning technique, right? And then we also talked about hierarchical clustering or hierarchical aglo clustering. I can't say the whole word. I'm sorry, everyone. But kind of benefits of that, because one thing with k-means is like we had to know what k was, and it turns out the best way to figure out what k is, we're essentially saying how many centroids we need in that algorithm, we basically have to just try it out multiple times, and a lot of like trial and error essentially. So hierarchical clustering is kind of nice because then we don't have to really worry too much about how many clusters we need to start off with. Is especially useful for things where you don't really know if there's going to be like necessarily like how many groups there are. It's also kind of a really great one for data that's already hierarchical. So like things that already have kind of like this hierarchy of like being stacked on top of each other, things that are very similar to each other, and then they get less similar. So I think I gave the example of like, evolutionary biology, where you might talk about like, a crocodile versus like a bird versus like a mammal, like they will have more similarities depending where they are on that hierarchy, basically where they branched off, which is perfect for like a dendrogram, which again was one of the things we used to visualize everything. So, oh my gosh, I just realized I have so many windows open. And there we go. I'm going to share my screen 1 second. Here we go. Okay. I got down to the base screen. All right. So today we're going to talk about, I think mentioned it just briefly when we did last time. And what we talked about was DBSCAN. So DBSCAN, I'll say, is not in the curriculum. It is another clustering algorithm. I'm actually going to pull up, it's a phone right here. Let's see if I can find it real quick. Here we go. I mentioned about this. This is from sklearn's, just like image about like, what's it called? All the different like algorithms, not all of them, but like a bunch of different algorithms. And one thing I didn't mention last time, I talked about how k-means doesn't do a very good job in deciding like these weird structures. There are ways you can do it. Does anyone got an idea like how you can adjust k-means so it does identify these sections separately? I'll give you guys a hint. Think what we did with support vector machines.
Is it the kernel trick?
Yeah, that's it. So kernel trick, yeah. So it turns out you can use the kernel trick to basically do k-means and basically treat these parts and put them into a separate, like a kernel trick basically allowing us to put into a separate dimension, right? Kind of adding extra complexity so we can identify those. So that's one way to kind of solve that. But you can see like it is kind of like some having to do those modifications, like it adds more complexity to our data set and our model. So I don't know. I think usually we tend to try to stay away from complexity, because what happens if we have something that's too complex? What does our model tend to do?
Overfit.
Overfit, right? So we always want the simplest possible model that still does a good job. Okay. So we're going to talk about DBSCAN though. And you can see here, this right here, DBSCAN on this column right here. Also is clustering, but you can see here, there's these dark spots. And that's because basically DBSCAN also has the factor of keeping in mind of like maybe there are things that are just essentially, what's it called? Outliers or noise or something that doesn't really belong to any one particular group. So that's a real plus for DBSCAN. And this is why I want to mention it, even though it's not in the curriculum. All right, so let me go pull up DBSCAN. Oh, my notebooks are loading slower and slower. Okay, so DBSCAN, a great mouthful, density-based spatial clustering of applications with noise. Right, no one ever says that, it's DBSCAN. So this kind of gives you an idea though, density-based spatial clustering. So density-based, things that are packed closer together. Spatial clustering, where they live like spatially, right? If they're close together, they'd be a cluster of applications. Well, it's just not, I think someone just put an A there, just to put an A in there. With noise. So basically when you have a situation where you possibly have noise in that. Okay. So it's not that scary after all. So again, it just allows us to find noise and outliers to be identified. Note that I do noise/outliers. I know usually I'll do this, but usually convention when we have like a slash, it means like either or. I I really should say noise and outliers. So those are completely separate different things, right? Because an outlier can be its own separate group in a way. It's like, oh, these are separate from the group, versus noise where it's like, oh, stuff that really shouldn't be considered maybe because it was incorrectly identified or something. So note those are slightly different things, but I'll use them interchangeably often. Okay, so conceptually, how does this all work, right? So we already seen a few ways of clustering. And essentially what's going to happen is very similar in the sense of like, no, I take it back. It's not similar at all. It's a little different. But the idea here is that we're going to kind of go through the different points and decide if they're one of three things. They're essentially a core point, a border point, or they'll end up being noise. And using those kind of like three classifications, we can then define what our different clusters are. So we're going to give a hyperparameter called epsilon here. So you can imagine this little tiny e, so if you're familiar with epsilon. Basically, you say, all right, there's an epsilon. We decide that ahead of time. That's a hyperparameter that we can kind of tune around and say, okay, are there a certain number of samples within this epsilon? So like we can say, for example, a min sample, which is also a hyperparameter. We say like, oh, there's only like, we want a min sample of 5 and our epsilon is like 0.02, whatever that means, right? Basically, it's the size of this circle. And we say, okay, take a point, say, and within that circle, are there so many samples in there? And if there are a certain minimum number, you're like, sweet, you little point right here are a core point. And then if you don't have enough, you say, okay, you're a border point. And essentially we use that kind of classification to build up essentially our different clusters. And it turns out border points with no cluster points end up being noise. So I realized I always gesture and I forget that I can just draw right here on top of here. But you can imagine like if we have a point, this is our kind of like our candidate point and say like, what are you? Like, are you a core point or border point, right? And then we have our different points. I'm gonna write it in like in purple here. So you can imagine like there's a border point here, or sorry, another point, and then you can imagine some other points right here. Okay, and then essentially say, okay, let's get our epsilon. Let's say an epsilon draws a circle around that blue point and say, okay, what's everything in here? And say, okay, there's 2 points. If our min sample was 3, then this would become a border point and say, hey, like you don't have enough to become a core point. But let's say we do actually have 3, so let's just draw a new one. Then this would become a core point and say, okay, cool. Like you are an important aspect of this, contribution to the cluster. Okay, essentially you should be a cluster because there are things that are near you. Okay, so, and that's more or less, and they go through each of those points. So what is really nice is that I don't have to draw all those out because someone made a great visualization of this. And I think I showed this last time too. Again, same author blog post person who wrote this as the one for k-means. So all the props to this person because they are awesome. So we'll go ahead and draw something like, let's do a simple Gaussian cluster or Gaussian mixture. And so this right here are different clusters, and note these red points are just going to describe our epsilon. So we can actually adjust the epsilon. You can see if I increase this epsilon, we get larger and larger circles, right? Basically, how big are these circles have to be? And you can see if I make it smaller, they have to be really close to each other. Okay, so I'll keep it about middle here. And then you can also see is that this is the number of minimum points. So you can see already like they already highlighted which ones would already classify, like looks good. And you can see that I can increase it all the way up to like, 5 points or something like that. So if I increase epsilon really large, but I need to include like, I don't know, 6 different points, not all of those might be, you can kind of see a little bit, there we go. Not all of them might be highlighted. Okay, and these two are hyperparameters that we can adjust to say, all right, how much do we expect these clusters to be close together? All right. Also note that this is a grid right here. So one thing we're doing too, instead of going through each individual point, one thing you can do is essentially have, depending how the algorithm's implemented, is you can essentially say, all right, are there any points within this centered right here? And go from that point. That's just another way to kind of applying the same algorithm. But you could also just look for a data point and see if there's anything nearby. Okay, makes sense so far? Cool. So what's nice now, we can just say, all right, go ahead and go. So what's gonna happen when I click go here, it's gonna identify these points here as like core points if there's enough minimum points around it. And then it'll go through and say, okay, all those points that are nearby, okay, these are all core points. And then it'll move on to those other points and go through and say, okay, these are core points or border points. And so I think it's easier to kind of see. So you can start right here and you can see basically all of these points are being identified as core points. Okay, and you can see some of them are not quite reached over here because they never clocked over here. And depending how big the epsilon is, I think we might actually get, in this case, all of them because our epsilon might be slightly too big. we'll actually get all of these as clusters, which actually we might want. But you can kind of see over on this side right here, I think these ones won't be marked as part. These will be noise. So you can see here is that this didn't have like that epsilon that was around here, didn't have enough points to be declared as a core point or as part of this cluster. So we might call these noise. Depending on your situation, you might actually want to expand epsilon or whatnot. Make sense? Okay. Does anyone want to kind of see a different distribution, kind of see how this works? Any questions on like what just happened? I know it went by really quickly watching all those little circles. Okay. So I'll just kind of emphasize one more time. So this one, you can't really see well. Well, actually, I'm going to use Pimply Smiley. So this one makes a lot of sense. So we can already see like the smiley face here, but there's some extra noise going on here. So I'm actually going to minimize my epsilon here, and I'm going to say 3 points. Again, these are hyperparameters you could tune, right? It depends. But the goal here is that we would probably hope to say this section, actually, I'm going to expand a little bit more. We kind of hope that this section, the outside, would be one group. This is its own group, this is its own group, this is its own group, and then identify the noise, okay? And so when you can see this first part, basically all of those things, again, are just going through each individual point and say, hey, if there are at least 3 points within that circle, we call that red. And you can see here is that it's going through kind of iterating all the way through the different points and say, okay, like if there are enough points that are nearby it, then we're going to mark you as blue. And you can see here is that this can also be like this one right here didn't have enough points, but it was within one of the core points that did have enough points near it. Does that make sense? So even though this point by itself doesn't have maybe like 3 points that are nearby it within that epsilon, it does have core points here that do have nearby within that reach. Versus these ones over here, they were never reached out by the core points over here. And you can see if I basically went over to this part, this won't be identified as its own group because essentially there aren't enough points within that epsilon to define it as its own separate group. Make sense? Okay. So
can you try rerunning it with as many minimum points as you can?
Yeah, so make a very large min points,
Yeah.
right? Yeah, so real quick before I do this, you can kind of see how I identified pretty decently, right? With epsilon 1.04 and min 0.3. What do you guys think? Adam, what do you think will happen if I do increase in min points as large as I possibly could? Would we get less groups or more groups?
Well, I'm thinking it's gonna be like there'll be less blue,
Okay.
less green, less yellow, less red.
Okay, so like maybe still 4 groups, but there's like less of those points within this grouping.
Yeah.
Okay, yeah, let's try it out, right? So let's do Simply Smiley, and then we had, well, keep it at, I think it was 1.04, right? I forgot. I think it was about that. Okay, well, no, I think it's about 1 something, so I'll keep it at 1. And then I'll adjust min points to 6. So as many as I possibly could, right? I think before we had 3. So if we do this now, what's going to happen is that we're going to keep, hopefully it was about the same epsilon. I might have, I can't remember exactly what epsilon is, but keeping the same epsilon, it needs at least 6 points in order to be considered as a core point, right? So what's going to happen is we're going to get less and less core points in here because they're not going to be connected. So what we'll probably do is that it's going to be more conservative on saying something that is a, what's it called, noise or not. So I think in this case, we would still have 4 groups, but we might actually have more noise than normal. So like, for example, this point might have been captured within that last time. And also, depending if this was a little bit more separated, we might actually get 2 different groups because maybe there wasn't like, if there's a little bit of a break between the 2 different groups. So I think here you can kind of see, I think last time we did have a couple like kind of spot out here. It might not be super obvious by itself, but that could be kind of the idea.
All right, thanks.
Yeah. But kind of going off this vein, I was actually going to ask kind of something similar. What would happen if we increase epsilon really, or what if we decrease epsilon really small?
Well, the border becomes smaller, so you would have less points that are selected. So
yeah, probably have less points, right? Yeah, because your epsilon's really small, and let's say we keep it at minimum 6 points. Well, there's a few of these that won't have that part in there, so they won't get marked as border or core points. So they'll probably have, you know, more noise, right? So we'll identify more noise. We also possibly could have more than that group. So if there's a break between here, like you can kind of see this jump right between the two. If our epsilon is really, really small, it might actually say, okay, like there's this essentially like a little bit of an island of points. So let's try to keep this. I'm going to try it one more time. So remember epsilon 1, min 0.6, we got this kind of picture. And let's go ahead and try it one more time. And let's do epsilon as small as we possibly can. So you can see very, very extreme. And I'm still going to keep it at 6 just to kind of keep it consistent. But you can already see this is probably not going to do very well. So let's see. Yeah, so right now it's looking at every individual point, and you can already see at the very extreme part, basically, there's nothing that is 6 points near here. So basically everything's getting marked as essentially noise. I actually don't know if I should let it keep going through. Might go through every single point, but you can kind of see the difference here. And I'm going to run this one more time. See if I can run this with slightly, there we go. Let's go like 0.5. And you can see here instead, now we're actually getting separate separate groups, because it's essentially saying, oh, it needs to be really, really dense in order for it to be considered a separate group. And so you can already see, instead of having 4 colors, we easily have like what, I don't know, like 9 different colors already, 10, and it's just increasing from there. So you can already see like basically adjusting your epsilon and your min points can really change how this goes through. Note that if I probably lowered this even further, like to like 2 points, we probably would get larger groups, like you can see already. Okay, cool. So hopefully that gives you a little idea of kind of conceptually like what's going on with DBSCAN. Makes sense? Any questions you guys have on how this algorithm works? How these hyperparameters can be adjusted? Yeah, pretty good, right? So that's a nice way to kind of see how this algorithm works. Again, read through this thing because it's not very long and it's fun to just play around with, and you can see it visually going through without you having to program it yourself. So really nice thing to have. Okay, so let me go back to our little thing, and we're going to see just how to implement this. And you're going to see I don't have as nice visuals as this one. I do have a little thing that I found online that we can pull up. But just to kind of show you a little bit what this looks like, we can essentially load in our data set, right? X in this case. I can go ahead and load this iris data set, and I can go ahead and do DBSCAN and do a dot fit. And basically this right here is all set to go, and I can test it on some testing data. Doing a dot predict, and that will basically provide saying, oh, what classes there are versus noise. But you can see already is that it's relatively straightforward to implement. You can see their hyperparameters are just essentially epsilon and min samples, though of course from sklearn you can probably see there's a few other things you can do. For example, like how do you measure how far something is. Also know there's a little bit of it's called a little bit of tweaking you can do too, like what kind of algorithm you use to like find what is near. So it turns out you can kind of define how that exactly is saying what is near itself. So there's some things you can adjust and play around with, and you can kind of get used to like what things might work for certain data sets. Okay, cool. Some advantages and disadvantages. So what's a clear advantage probably from this compared to everything we've seen for clustering? So one thing, like everyone's got something right now, but one thing, right, is that it can identify noise, right? That's not something we could find before with the other clusters, at least not directly with the algorithm. It's meant to be able to find that noise and stuff like that. So we don't need to, we can deal with this noise and outliers and not just like say, oh, is it robust against noise and outliers? It can actually identify, say, hey, these are noise and outliers, which can be really important. Again, going back to the one I showed with k-means, that little graphic from sklearn. Come on there we go. Again, is that like none of these algorithms except for like DBSCAN and optics, which is kind of works similar to like DBSCAN, but actually identify this extra fuzz essentially out here as noise. Now, you can debate saying, is this actually noise or should it be part of the group? But the fact is that it can actually identify these parts. Okay. Some other advantages is that it's flexible in shape. So you saw like with the smiley face, for example, is that it was able to identify those groups really easily compared to k-means, which we would have a harder time, or we have to do some tricks like, the kernel trick or something like that. Also, again, one thing that's really nice compared to something like k-means is similar to hierarchical clustering, is that we don't need to know how many clusters there are in our data set. Essentially, what defines a cluster is essentially how dense should it be. how basically based on epsilon and then how many minimum samples we need to be in that group. So what's nice is that it's kind of independent from you knowing how many clusters there are to begin with. Okay. Some disadvantage is that the border can be reached from 2 different clusters. So one thing is that like as you get 2 different clusters and they get closer to this edge part, it can basically be reached out from either one, and it might not be clear which one's which. So sometimes you might get, depending on like, you know, if you started on the right side or started on the left side, you might get like these middle points to belong with, what's it called? Like class A. And then if you tried it again, it might actually be class B. So those middle points can be kind of a fuzzy part for borders. Usually the solution to this essentially is adjusting the hyperparameter. So you either count that as noise or like, you know, noise or outliers, but that might not always be the best thing. So borders isn't really the best thing for it to be used. It's really meant a lot for like clustering, saying, okay, what's the density that's going through here? And then one problem too is that since it's talking about density, remember, it doesn't really care about how many clusters there are. It really depends on saying the epsilon and min samples. Well, it assumes the density is the same for all groups. So if a cluster is actually less dense, right, but they should still be similar to each other, but they're just not as densely packed, it'll be identified as maybe multiple groups, which might not be what you will be looking for. So that's some of the disadvantages in here. Okay. Cool. Any questions on these advantages, disadvantages when you would use DBSCAN versus some other algorithm? Yeah, look good. Cool. I was seeing if there was something that would have, oh, here you can see the density bar. So this is what I mentioned about like different densities. So as you kind of go out, you can kind of see that this isn't going to be identified as easily because it's a different density from the original here. So I probably can't speed this up, but you can kind of imagine how that looks through. Okay. I could just do this for hours, just play around with this little graphic. I don't know about you guys. Anyway, I'll stop it here, or stop that scan thing. Okay, so that kind of finishes up our stuff on clustering. Are there any overall questions about clustering, unsupervised learning, on, I don't know, when it's used, applications, or anything like that? All right, pretty good.